We are rolling.
So, when we put a system of charges together, it takes energy to put that system of charges together, and there's potential energy stored in that system that we put together. And we can, for each charge that we put into a system, do the integral. Work is equal to the integral of force. Got it into the path from the initial point to the final point, and that force would be related to the electric field. It might as well write it in. Integral. That, all right? And the potential energy that's stored in the system is equal to the work. Got to make sure I get the right sign here. I'll leave it like that, right? We have to put, potential energy stored in the system is equal to the work that we do on the system, okay? So for a whole bunch of charges that we put together then, the potential energy that we've stored in the system is, from physics 2, n charges, it. Okay. Note the omission here of I equal to j. That is that we've excluded the self energy of a charge itself upon itself. And that's because we've considered this system to be a system of point charges. And by point charge, I mean a charge with no volume. So the charge is represented by a delta function at 0, and therefore the self-energy stored in the field of a point charge, we'll come back to the field in a minute, is infinite. Okay? Field is infinite at the source. Okay? So we've excluded the charge from itself here.
Is that the Q prime?
This is apparently a problem with the board.
Is it supposed to be, that was Q dot Q.
Yeah. Whatever. Okay. If we're dealing with a continuous distribution of charge, we actually don't have the self-energy problem. Because if we work out how much energy it takes to put together the continuous distribution, the charge interacting with itself is not infinite. It's distributed. So we can show that, but I'm not going to show it because it's going to take 20 minutes for today's lecture. So if you have a continuous distribution of charge, I've got my, now I do have an R prime here, rho of R prime. Those are not two different charges. That's basically taking a charge distribution and comparing its distance to other charges in the same distribution. Over all the charges, and the half because we don't want to double count. Same here. The half here is because we don't want to double count. We've taken the potential energy between this charge and then that charge and this charge. So we counted everything twice. Same deal here. We've counted them both twice. Okay? What's wrong? Well, there's something wrong or funny. Or
The double volume integral is funny.
double volume. Oh, you just don't like it.
Not amusing.
Okay, that's good.
There's a pop culture reference in there.
I like that. All right. But if we look at, let's say, this little bit here, all right, we see that that's the potential due to at point R, due to a charge at point R prime. Okay? So this actually is 1/2 single integral rho of R phi of R. We need one integral in volume. We did one of them already because that one's just potential. Okay? So I've got the charge distribution due to the potential of that same charge distribution. Now we can use that the divergence of the electric field is equal to 4 pi rho. All the charge, bound and free in a problem. Okay? And so this is actually 1/2 integral divergence of the electric field is that. Okay? That's a volume integral. And I can integrate by parts, or use an integration by parts trick here, right? And this, oh, I lost a 4 pi. There's 1 over 4 pi that went in there, so it makes 1 over 8 pi. So integrating by parts, 8 pi integral, divergence of E phi, whatever you might think that is, right? Minus E dot grad phi. Okay? So now my integral's got 2 parts. Now, if the overall charge distribution is finite, then, and I want to find the total energy in the system, I integrate over all volume, right? Then this term we can argue is going to go to 0. Because remember, I'll be explicit, the integral of the divergence is the flux through the surface. Shift phi over here. Okay? But for a finite charge distribution and integrating over all volume, this is 0. And the reason that this is 0 is because the slowest that the potential is going to drop is for a monopole. The monopole term, right? So that's like 1 over r. And the slowest that the electric field is going to drop is 1 over r squared. It could go faster if I've got dipoles or quadrupoles, right? Only dipoles or only quadrupoles. It could go faster. So this term here is going to drop faster than 1 over r cubed. So I'll just put a plus in there, right? And this term here only goes up as r squared. So I make the system big enough, and the surface integral is going to be 0. Okay? So overall volume, this is going to reduce to, I have just enough room. Oops. 1 over 8 pi, integral over the volume. Whew. I've got minus E dot grad phi. Anybody know what grad phi is?
E.
There, minus E.
We've got the minus sign already there.
And I had a minus sign, and now the minus sign is gone. Evan?
For the argument you used about gradient of E5, how do you correct for that when you get down to the quantum scale? Because I assume once you're super small, then it no longer works.
Yes. Right here, there's no problem because, well, not no problem. It's fine right down to the Planck scale.
Okay.
All right. And then I have no idea what happens there, and no one does, so let's just treat it as though it's not there.
Okay.
But in a moment, I'm going to make a correction to this for materials with dielectrics.
Okay.
Right, so if we were going to put a charge, distribute charges together in a dielectric, then what's going to happen? And there, we can only talk about the macroscopic fields. And once you get down below, a distance of let's say several atoms across, you can't apply the dielectric function of this. Yeah.
If your potential, if it falls off as exactly 1 over r cubed times r squared, doesn't that become 1 over r, which diverges when you integrate over it? Is it 1 over r, like, doesn't that diverge? Or am I thinking?
I'm going to say no, but I don't have off the top of my head argument right now. The A is r squared.
Is it because it's a surface integral?
I know. Choosing to choose a larger surface. I know.
Choose a larger surface. Who said that?
No.
Yeah.
I know why. When you're doing the surface integral, you're not integrating over r. You're only integrating.
Yeah, you're only integrating
the
over
angles.
theta and phi.
And so you get 1 over r on the outside of that, times constants times the solid angle, and that will zero out.
Yeah, that was actually a jig and not a.
Mexican.
No, wait a minute. It could be a Mexican hat. Oh, yes. But what I was actually thinking of
Irish
was
Stomp.
no.
Stomp the yard.
Irish.
Riverdale.
Hang up
I facepalm so hard.
Yeah, it's almost like, what's the name of that game? Charades.
Are those two E's the same?
Is that working?
Yes.
Oh, crap.
Can you take a still image? No, find it. Take a still image of that.
Of him doing that?
Yeah.
It wasn't aimed at him.
No.
Him here.
I'm shooting the board. It isn't on. I wasn't aiming it at him.
Oh.
It was on the board, which is the important part.
That one he's
Not quite as smart.
This is a dielectric. Okay, in a dielectric, I'm going to be finished in a minute, all right? So in a dielectric, I have a whole page of notes that I am not going to go through. Here's what I'm going to state. On a macroscopic scale, so that we're not worried about atoms, we're talking about the average behavior of the dielectric. The energy density in the dielectric, or sorry, the energy in the dielectric is 1 over 8 pi integral dielectric. Oh, this is for a linear dielectric. Epsilon E squared. And to indicate that we have to worry about the macroscopic and not the interatomic fields, I'm just going to put like a little bar there to indicate average it appropriately. Okay, so you have to think about it, about the appropriate averaging. Yes.
Is that DS or DA or DV?
Oh, dV over the volume. Right. The local energy density in both of these cases, I could write, is energy density is 1 over 8 pi E dot D. And for a linear dielectric, it's epsilon E squared. Okay, that's the energy stored in the field for a continuous charge distribution. If you have point charges, so quantum mechanical point charges, the electron, for example, poses a real problem to us here. Because as far as we know, the electron is a point charge. And if we were to attempt to actually compute the field right up to the 0 dimension of the point charge, we're going to get an infinite field there, right? And the integral actually turns out to be infinite as well. So we actually don't, to be honest, we don't have a full solution. We don't have a consistent solution to the problem of the infinite self-energy of the electron or of any quantum mechanical fundamental particle, right? And that's in part why string theory got proposed. That gives you a length scale down to which we could do the computation. And almost all of the time what we're doing is comparing the energy of this system versus the energy of that system. And as long as you don't annihilate fundamental charges, the energy of this system and that system will always subtract off the near infinities of the charge, the field of the charges themselves, right? So what I've written here is all fine for non-point charges, okay? If you've got point charges in the problem, then you have to somehow exclude a small volume around those point charges, at least so that you can appropriately calculate some total energy. Okay, that's it then. Okay.
Can we get you to do that one more time on camera?
No.